Pinocchio's nose grows when he tells a lie. Now imagine he says, "My nose will now grow." What happens? If his nose does grow, it means he was telling the truth. But if he was telling the truth, his nose shouldn't have grown, because it only grows when he lies. However, if it doesn't grow, then he must have been lying. But if he was lying, his nose should have grown. Either way, we end up in an endless loop. This paradox is a variation of the classic liar's paradox. This statement is false. It forces us to confront the weird nature of self-referential statements. A truth that creates a contradiction cannot be true, but a lie that contradicts itself also cannot be a lie. Philosophically, this paradox highlights the limitations of binary truth values. Some logical systems, like fuzzy logic, propose that truth exists on a spectrum rather than a strict true-false dichotomy. In other words, statements like Pinocchio's may exist in an undefined state rather than breaking logic entirely. It also makes us rethink how language works, especially when applied to paradoxical conditions. Pinocchio's problem may be fictional, but it exposes real issues in logic. The Omnipotence Catch-22. The Omnipotence Paradox questions the very nature of unlimited power. If a being is truly all-powerful, can it create a rock so heavy that it cannot lift it? If yes, then it is limited, because it cannot lift the rock. If no, then it is still limited, because there is something it cannot create. Either way, omnipotence seems self-contradictory. This paradox has been debated in philosophy and theology for centuries. Some argue that true omnipotence doesn't include the ability to do the logically impossible. Others propose that an omnipotent being could create such a rock and still lift it by redefining physical laws at will. Another perspective is that omnipotence must be consistent with itself, meaning an all-powerful being would not engage in paradoxical actions. The paradox highlights how absolute concepts like all-powerful may be incoherent when analysed logically. It also raises deeper questions about free will, logic, and the nature of divine power. If omnipotence includes logical contradiction, then all rules break down. If it doesn't, then it has limits. Either way, the concept forces us to reconsider what power really means. It's a perfect example of how language can trap us in contradictions. The Borel Paradox. The Borel Paradox comes from probability theory and challenges our intuition about conditional probabilities. It essentially shows that the probability of an event can depend on how we define our conditions, making probability seem arbitrary in certain cases. Here's an example. Imagine you pick a random point on a sphere. If I ask, what's the probability that this point is on a specific meridian, a line of longitude? The answer is 0. Since there are infinitely many meridians, the probability of hitting any specific one is almost impossible. But now suppose I first tell you that the point is on the equator. Suddenly, the probability of it being on any given meridian is not 0. It's now a well-defined fraction of 360 degrees. This means the way we set conditions changes the probability itself. This paradox matters in fields like statistics, machine learning, and Bayesian reasoning. It challenges our assumptions about randomness and prior knowledge. If probability depends on framing, how much of it is an inherent property of reality versus just a mathematical construct? It's a reminder that probability isn't always as objective as we think. The Hypergame Paradox. Hypergame is a game where the first player chooses any finite game and then both players play that game. At first, this sounds reasonable. If all chosen games end, Hypergame should always end. But here's the twist. What if the first player chooses Hypergame itself as the game? Now the game becomes an infinite loop because it never resolves into a finite game. This creates a contradiction. Hypergame should only allow finite games, yet it permits a choice that makes it infinite. This paradox is similar to the liar's paradox and Russell's paradox in set theory, where a set that contains all sets leads to contradictions. It also relates to Gödel's incompleteness theorem, which shows that some logical systems contain unavoidable self-referential loops. Hypergame exposes a deep problem in defining rules. When rules refer to themselves, contradictions can emerge. it also raises philosophical questions. How do we define what is finite when a rule allows infinite recursion? In real life, this applies to paradoxes in bureaucracy, legal systems, and even AI decision-making, where self-referential rules can create logical traps. It's a deceptively simple idea that reveals a profound issue in logic, the predictability paradox. If you predict that someone will do something, can they choose to act differently just to prove you wrong? If they can, then the prediction was false, which means future events are not fully predictable. But if they can't, it implies they have no real free will, just a predetermined path they must follow. This paradox appears in time travel stories, psychology, and even physics. If everything is determined by prior causes, then in theory, a perfect predictor, like a super advanced AI, could calculate all future actions. But if the predicted person is aware of this, they might deliberately act unpredictably, creating a feedback loop where perfect prediction becomes impossible. In philosophy, this relates to the debate between free will and determinism. If everything follows cause and effect, then maybe there's no true choice. But if free will exists, then no system, not even a superintelligence, can perfectly predict the future. This paradox has real-world consequences. In economics and AI, accurate predictions can sometimes alter outcomes, like in stock markets or strategic games. It also raises the question, if we knew our own future, would we still have the power to change it? It's a paradox that challenges our very sense of control. The infinite lottery paradox. Imagine a lottery where there are infinitely many tickets, numbered 1, 2, 3, and so on. One ticket must be chosen randomly, and every individual ticket has a probability of 0 of being picked, because in an infinite set, any single outcome is infinitely small. But here's the paradox: a ticket must be chosen. If every ticket has 0 probability of being chosen, then how can one be selected? Shouldn't the probability of picking any ticket also be 0, making it impossible? This paradox exposes a flaw in our intuition about infinity and probability. In a finite lottery, each ticket has a non-zero chance of winning. But in an infinite lottery, the concept of probability breaks down in a way that challenges the foundations of mathematical logic. It raises deep questions about how probability works in infinite sets. Some argue that rather than having a probability of 0, each ticket should have an infinitesimal probability, a concept not normally used in standard probability theory. This paradox is important in physics, especially in discussions of infinite universes and quantum mechanics, where infinitely many possibilities exist, yet some outcomes must occur. The unexpected hanging paradox. A judge tells a prisoner, "You will be hanged at noon on a weekday next week, but the day will be a surprise. You won't know the day until the executioner arrives." The prisoner thinks, "If they wait until Friday, I'll know by Thursday night, so it can't be Friday. But if Friday is ruled out, then Thursday becomes predictable, so it can't be Thursday either. Applying this logic, every day is ruled out, therefore I won't be executed. But then on a random day, the executioner arrives. The prisoner is completely surprised. This paradox challenges our ideas of self-referential logic. The prisoner's reasoning seems flawless, but it leads to an incorrect conclusion. The core issue is the assumption that knowledge can eliminate all possibilities. In reality, the paradox shows that human reasoning has limits. Just because something appears logically impossible doesn't mean it can't happen. This paradox is often compared to Gödel's incompleteness theorem, which shows that even formal logical systems can contain contradictions. It's also relevant in game theory, AI, and even financial markets, where perfect knowledge doesn't always guarantee the expected outcome. The Borel Paradox. Consider the phrase, "the smallest positive number that cannot be described in fewer than 20 words." This phrase itself is only 15 words long, yet it describes a number that supposedly cannot be described in fewer than 20 words. That's a contradiction. The Borel Paradox comes from self-referential definitions. It exposes a flaw in the way we use natural language to describe mathematical ideas. We assume that defining something is always valid, but this paradox shows that some definitions can lead to contradictions. This paradox is closely related to Richard's paradox and the liar's paradox. It also connects to fundamental issues in computer science, especially in algorithmic complexity. Can we always describe something in a finite, predictable way? Gödel's incompleteness theorem and Turing's halting problem show that some truths cannot be formally proven, much like how the Berry paradox shows that some definitions collapse under scrutiny. The deeper takeaway is that natural language, even when it seems precise, can create contradictions that mathematics alone cannot resolve. It reveals how the way we describe things affects what we think is real or possible. The Yablo's Paradox. Yablo's paradox is an infinite version of the liar's paradox, but without self-reference. Imagine an infinite sequence of statements. All statements after this one are false. All statements after this one are false. All statements after this one are false. And so on forever. Now, if the first statement is true, then every statement after it must be false. But if the second statement is false, then the third must be true, which creates a contradiction. No consistent truth assignment works, yet no single statement refers to itself directly. Unlike the classic liar's paradox, this statement is false. This paradox challenges the idea that contradictions require self-reference. It suggests that infinite sequences can produce logical paradoxes, even when individual statements seem fine. Yablo's paradox is important in logic and philosophy because it shows how paradoxes can arise purely from structure, not just self-referential loops. It has also influenced research in mathematics, especially in theories about infinite sequences and formal logic systems. The paradox raises a bigger question. If logic itself can generate paradoxes without self-reference, how much can we really trust formal reasoning? The Quine Paradox. The Quine Paradox is a self-referential puzzle involving a statement that describes itself in an unexpected way. Yields falsehood when preceded by its quotation. Yields falsehood when preceded by its quotation. At first this looks like nonsense, but let's break it down. If we take the phrase yields falsehood when preceded by its quotation and put it before itself in quotes, it should yield falsehood, meaning it should be false. But if it's false, then the original statement must be true, which is contradictory. This paradox is a variation of the liar's paradox, but it's uniquely constructed to collapse under its own definition. It plays with self-reference in a way that highlights how language and meaning can be manipulated. It's named after logician Willard van Orman Quine, who studied self-reference in formal logic. The paradox connects to Gödel's incompleteness theorem and Tarski's undefinability theorem, both of which show that formal mathematical systems have limits. The Quine paradox is also important in programming and artificial intelligence, where self-replicating or self-referential code, like Quine's in programming, can challenge normal logic. It reminds us that meaning and reference are not always as straightforward as they appear. The Hempel's paradox, Raven's paradox. This paradox challenges the way we think about evidence and confirmation in logic. It starts with a simple statement. All ravens are black. Logically, this means that if something is not black, it cannot be a raven. So if we see a red apple, it technically confirms our statement, because the apple is not a black raven. But that feels absurd. How can observing apples, grass, or blue cars tell us anything about ravens? Yet according to formal logic, any instance of not black things being not ravens strengthens the rule that all ravens are black. The paradox exposes a flaw in our intuition about inductive reasoning. Normally we assume that confirming a rule requires directly observing examples, e.g. seeing many black ravens. But logic suggests that indirect observations, e.g. seeing non-black non-ravens, also count. This paradox plays a key role in philosophy of science. It questions how we define scientific evidence. If we accept its logic, then absurd things, like looking at bananas, should help confirm biological truths about birds. It forces us to rethink how knowledge is built. Are all forms of evidence equal, or do some just feel more valid? The card paradox. The card paradox plays with self-reference and contradiction, much like the liar's paradox. Imagine you have a card with two statements written on it. Front. The statement on the back of this card is true. Back. The statement on the front of this card is false. Now let's analyse it. If the front is true, then the back must also be true. But the back says the front is false. Contradiction. If the front is false, then the back must also be false. But if the back is false, then the front shouldn't be true either. No consistent truth assignment works. The paradox loops endlessly. This highlights the danger of self-referential statements. They create logical traps where normal reasoning collapses. It's similar to the classic liar's paradox, but structured to look deceptively simple. Philosophers and logicians use this paradox to study the limits of truth systems. It also appears in computing, where circular logic can crash programs. It's a perfect example of how words can twist into contradictions, making something impossible, despite seeming logical at first glance. The paradox of the preface. Imagine an author writes a book filled with factual claims. Before publishing, they add a preface. Despite my best efforts, I might have made some mistakes in this book. Here's the paradox. If the author believes everything in the book is true, then they shouldn't think there are mistakes. But if they believe they might be wrong, then they don't fully believe their own statements. This exposes a contradiction in everyday reasoning. We often trust our beliefs, yet acknowledge that we could be mistaken. The paradox asks, can we logically hold both views at once? In philosophy, this challenges ideas about rationality. Should a rational person always believe what they write, or must they admit fallibility? If so, then does that mean they don't fully believe their own claims? This paradox applies to science, law, and journalism, fields where experts make strong claims but always leave room for error. It highlights the tension between certainty and intellectual humility. It suggests that contradiction isn't always irrational. Sometimes it's just human nature. The shoe switch paradox. This paradox plays with probability and counterintuitive logic. Suppose you randomly grab two shoes from a pile. The first shoe has a 50% chance of being a left shoe, and the second shoe has a 50% chance as well. So shouldn't the probability of getting a matching pair be 50% times 50% equals 25%? That seems reasonable, but it's wrong. In reality, the probability of getting a matching pair is 50%, not 25%. Why? Because once you pick the first shoe, the second shoe's probability is not independent. If the first shoe is left, the second shoe must be right, and vice versa. The two events are linked, meaning the second choice isn't random in the same way as the first. This paradox exposes how misunderstandings in probability can lead to false conclusions. It's a common mistake in gambling, statistics, and even AI decision-making. It reminds us that probability isn't always about isolated numbers. It depends on context and dependencies between events. The forest fire paradox. Imagine a vast forest that has been completely untouched by fire for centuries. Now ask yourself, is this proof that the forest is safe from fires, or is it proof that it is overdue for a massive fire? This paradox highlights how the absence of evidence can be misleading. In a way, long-term safety creates the conditions for disaster. Without small, controlled fires clearing the underbrush, fuel builds up, making the eventual fire far worse. This applies to many real-world systems. Economies. A market that has never crashed may seem stable, but it could be due for a major collapse. Health. If someone never gets sick, their immune system might be unprepared for a real threat. Technology. A system with no failures might be accumulating hidden risks, making its eventual breakdown catastrophic. The paradox teaches us that stability can be deceptive. Just because something has never happened doesn't mean it won't. In fact, it might be more likely. It's a reminder that risk doesn't disappear just because we don't see it. Often it grows stronger in the shadows. The Benford's law paradox. Benford's law states that in many naturally occurring datasets, the first digit of numbers is more likely to be small. For example, in financial records, populations, and even lengths of rivers, about 30% of numbers start with 1, while only about 5% start with 9. This seems completely counterintuitive. Shouldn't all digits be equally likely? The paradox is that we expect numbers to be random, but reality doesn't work that way. The reason is that numbers in many datasets grow exponentially rather than linearly. If you look at real-world data, like financial transactions or stock prices, the numbers don't appear evenly distributed. Instead, they cluster around smaller values and gradually spread out. This paradox is widely used in fraud detection. If someone fabricates financial data, they tend to make digits evenly distributed, which contradicts Benford's law. Auditors use this to catch tax evasion, election fraud, and even scientific misconduct. It's a paradox because it defies intuition. People assume randomness means uniformity, but true randomness in real-world numbers follows a skewed pattern. It's a reminder that randomness and predictability can coexist in unexpected ways. The Galileo's Paradox. Galileo's paradox reveals a strange property of infinity. Consider the set of all natural numbers. 1, 1, 2, 3, 4, 5. Now consider the set of perfect squares. 1, 1, 4, 9, 16, 25. There are obviously fewer squares than natural numbers, right? But wait, each square corresponds to exactly one natural number. This means the two sets have a one-to-one correspondence. So which is it? Do the squares make up a smaller subset, or are they just as infinite as the natural numbers? The paradox shows that infinity doesn't work like regular numbers. In finite terms, a subset must be smaller than the whole. But in infinity, a subset can be just as large as the full set. This insight led to deeper discoveries in set theory. Mathematician Georg Cantor later formalized different sizes of infinity, showing that while some infinite sets are countable, others, like real numbers, are uncountably infinite. Galileo's paradox challenges our basic intuition, proving that infinity is far stranger than we imagine. The Borel-Kolmogorov Paradox. This paradox challenges how conditional probability works in continuous systems. Imagine you select a random point on a sphere. Now you want to calculate the probability of it landing on a specific line of longitude. The problem: if you pick a random point on the sphere, the chance of hitting any single longitude line is 0, because there are infinitely many of them. However, if I tell you that the point is already on the equator, suddenly the probability of it being on a specific longitude is not 0. This suggests that probability changes depending on how we frame the problem. If we condition on different variables, we can make seemingly impossible events, probability equals 0, suddenly have real probability. This paradox has real-world consequences in Bayesian probability, physics, and statistics. It raises the question: how much does probability depend on perspective? If probability can shift depending on context, then how much of it is truly objective? It suggests that probability is not just a measure of randomness, but also a reflection of the way we frame information. The whole argument paradox. The whole argument was introduced by Einstein while developing general relativity. It questions whether space-time has an independent existence beyond the events occurring within it. Imagine we take all physical matter out of a region of space, creating a whole. Does the space inside the whole still exist, even if nothing is there? If it does, then space must be something real and independent. If it doesn't, then space is just a mathematical tool we use to describe physical interactions. The paradox arises when trying to assign physical meaning to coordinate systems. In classical physics, space is just an empty stage where things happen. But in relativity, space-time itself can bend, stretch, and be influenced by mass. This means that if we try to describe empty space, we might not be describing anything real at all. This paradox plays a role in quantum gravity and black hole physics. It forces us to ask, is space-time a real entity, or just a way we organize our understanding of the universe? The paradox shows how deeply our assumptions about space and reality can be challenged when we try to build a fundamental theory of everything. The Nocebo Paradox. The placebo effect is well known. People experience real improvements in health simply because they believe a treatment will work. But the nocebo effect is its dark twin. People experience negative effects simply because they expect something to harm them. The paradox is this: if belief alone can cause harm, then does that mean knowing too much about risks actually makes people sicker? For example, studies show that when patients are told about possible side effects of a medication, they are more likely to experience them, even if they're given a sugar pill. This means that just by warning people, we might be causing harm. This raises ethical questions in medicine. Doctors must inform patients of risks, but if that information increases suffering, is it always the right thing to do? The Nocebo Paradox also applies to social psychology. Widespread fear about illnesses, economic crashes, or technological dangers might make these problems worse, simply because people expect them. It's a powerful reminder that our minds can shape our physical reality, sometimes in ways that completely defy logic. The Borel-Cantelli Lemma Paradox. The Borel-Cantelli lemma deals with probability and infinite events. It suggests that if you have an infinite number of events with small probabilities, some will still happen with certainty. Here's the paradox. Imagine you flip a fair coin infinitely. The probability of any one specific sequence, like all heads, is 0. But the probability that some highly unlikely event happens, such as infinitely many heads appearing at some point, is actually 1. This challenges our intuition. How can something have a probability of 0 but still be guaranteed to occur? The paradox arises because probability 0 doesn't always mean impossible in infinite settings. This is relevant in real-world applications like stock market crashes, genetic mutations, and physics. While individual extreme events are unlikely, over an infinite timeline, they must happen. It teaches us that probability behaves strangely at infinity. What seems impossible eventually becomes inevitable. The Measure Zero Paradox. The Measure Zero Paradox is a deep mathematical issue about size and probability. It states that some infinitely large sets have zero measure, meaning they take up no space, yet they still exist. Imagine a dartboard where the probability of hitting an exact point, like 0.5, is 0. But the dart must hit some point. The paradox is that each individual point has 0 probability, yet collectively they form a certainty. This breaks our normal understanding of probability. If each possible outcome has 0 chance, how can an event still be guaranteed to occur? This paradox has implications in quantum mechanics, where particles exist in probability distributions, and in artificial intelligence, where infinite possibilities must be managed. It forces us to rethink what 0 probability really means. It doesn't always mean something won't happen, just that it can't be measured in the usual way. The new riddle of induction. Goodman's Paradox. Goodman's paradox challenges how we define laws of nature versus arbitrary observations. Imagine this rule. All emeralds are green. Now define a new property called GRU. An object is GRU if it is green before 2050, but blue after 2050. By this logic, all emeralds so far are GRU as well as green. So why do we believe they'll stay green instead of turning blue? Both rules fit past observations, but only one seems natural. The paradox questions how we justify scientific predictions. Why do we trust some patterns and not others? We assume emeralds will stay green because we're used to them being green. But is that logic actually valid? Goodman's paradox is central to the philosophy of science. It suggests that our reasoning might be based on habits rather than objective truth. It's a reminder that what we call obvious is often just what we've been conditioned to expect. The St. Petersburg Paradox. This paradox exposes a flaw in how we value risky decisions. Imagine a game where you flip a coin until you get heads. The payout is 2 to the power of n, where n is the number of flips. If you get heads on the first flip, you win $2. If it takes 2 flips, you win $4. If it takes 3 flips, you win $8. The expected value of this game is infinite because every additional flip doubles the payout. Yet the chance of reaching that flip drops by half. So in theory, you should be willing to pay any price to play this game. But in reality, people wouldn't pay much. Why? Because even though the average payout is infinite, the probability of extreme payouts is tiny. This exposes a gap between mathematical expectation and human decision-making. It highlights real-world issues like insurance, gambling, and investing, where theoretical values don't always match practical decisions. It shows that people don't just calculate expected value, they weigh risk, uncertainty, and psychological factors. The Sybil's prophecy paradox. This paradox explores how knowing the future can change it. Imagine a prophet, Sybil, who predicts someone will make a specific choice. The paradox is, if the person believes the prophecy, they might act to fulfill it, making it true. If they try to resist the prophecy, they may end up causing it in a different way. This paradox appears in stories like Oedipus Rex, where trying to escape fate leads to fulfilling it. It also appears in time travel paradoxes, where knowledge of the future limits free will. The deeper issue is whether knowing a future event makes it unavoidable. If it's truly inevitable, then there's no free choice. But if it can be changed, then was it ever really the future at all? This paradox is relevant in psychology, self-fulfilling prophecies, economics, market predictions, and even quantum mechanics, where observation alters reality. It raises the unsettling question, if you knew your fate, could you actually change it? The prisoner's dilemma. Paradox. The prisoner's dilemma is a classic paradox in game theory that challenges our understanding of rational decision-making. 2 prisoners are arrested and put in separate rooms. Each has 2 choices: stay silent, cooperate, betray the other, defect. The outcomes? If both stay silent, they each get a light sentence, 1 year. If one betrays and the other stays silent, the betrayer goes free and the silent one gets 5 years. If both betray each other, they both get 3 years. Logically, each prisoner should betray because it guarantees a better outcome, regardless of what the other does. But if both betray, they end up worse off than if they had cooperated. This paradox reveals a deep flaw in human decision-making. Rational self-interest often leads to worse outcomes for everyone. It appears in economics, politics, and even evolution, where individuals or nations acting selfishly can create bad situations for all. It questions whether pure rationality always leads to the best decisions. Sometimes trust and cooperation are more beneficial than logic alone. The Sleeping Beauty Paradox. Sleeping Beauty is put to sleep on Sunday. A fair coin is flipped. If heads, she is woken up on Monday and never again. If tails, she is woken up on Monday, then put back to sleep and woken again on Tuesday. Each time she wakes up, her memory is erased, so she never knows which day it is. When she wakes up, she is asked, what is the probability that the coin landed heads? The 1/2 argument. The coin was fair, so the chance of heads is still 50%. The 1/3 argument. There are 3 possible wake-ups: Monday, heads, Monday, tails, Tuesday, tails. Only one corresponds to heads, so the probability must be 1/3. Philosophers and mathematicians still debate the correct answer. The paradox questions how probability works when observers have incomplete information. It has implications in Bayesian reasoning, AI predictions, and even quantum mechanics, where outcomes depend on observer knowledge. It forces us to rethink what probability means. Does it reflect objective reality or just our perspective on it? The Twin Paradox. The Twin Paradox is a thought experiment in special relativity. Imagine 2 twins. One stays on Earth, the other travels to space at near light speed and returns. Due to time dilation, The travelling twin ages more slowly than the twin who stayed behind. When they reunite, the space-travelling twin is younger. The paradox is, from the traveller's point of view, shouldn't the Earth twin also be moving? Why doesn't the Earth twin experience time dilation too? The resolution lies in relativity. The travelling twin accelerates to turn around, which breaks the symmetry. In physics, acceleration changes the reference frame, making the effects asymmetrical. This paradox isn't just theoretical. It has been confirmed using atomic clocks on fast-moving airplanes. It has real-world implications for GPS satellites, which must account for time dilation to provide accurate positioning. The twin paradox forces us to rethink time, not as a universal constant, but as something relative to motion and gravity. The Bootstrap Paradox. The Bootstrap Paradox is a time travel paradox where an object or piece of information has no clear origin. Example: a scientist from the future goes back in time and gives Shakespeare a copy of his plays. Shakespeare copies them and publishes them as his own. Centuries later, the scientist reads the plays, copies them, and takes them back in time. Who originally wrote them? The paradox shows a causal loop, where something exists without ever being created. This violates the normal flow of cause and effect. It appears in many time travel stories, such as a time traveller teaching Einstein about relativity before Einstein discovers it himself. Some physicists speculate that closed time loops could exist under certain conditions, but they raise huge questions about free will, information, and reality itself. The Bootstrap Paradox challenges our understanding of causality. Can something exist simply because it always has? The Hutton's Paradox. Hutton's Paradox is about deep time and our perception of history. It comes from James Hutton, the geologist who first proposed that Earth is vastly older than previously thought. The paradox is this: if the Earth has existed for an unimaginably long time, why does it still show signs of youth? Shouldn't erosion and natural processes have flattened everything by now? Hutton's answer was that Earth operates in cycles. Mountains erode, but new ones rise. Rivers carve valleys, but tectonic shifts create new land. This idea led to uniformitarianism, the principle that Earth's processes are ongoing and endless. This paradox is a key issue in cosmology as well. If the universe is so old, why do stars still burn? Why hasn't everything reached thermal equilibrium? The answer involves constant renewal. Just like Earth, the universe isn't static. Hutton's paradox forces us to rethink time. Just because something is old doesn't mean it's worn out. It might be part of a cycle we barely understand. The symmetry breaking paradox. Symmetry breaking is a fundamental concept in physics, but it leads to a strange paradox. If a system starts completely symmetrical, how does it decide which way to break? Consider a pencil balanced perfectly on its tip. In theory, it should stay upright forever because all forces are equal. But in reality, it always falls, choosing a random direction. The paradox is, what determined the direction? If the system was truly symmetrical, no direction should be preferred. Yet something causes the symmetry to break. In physics, this happens in phase transitions, like how water molecules arrange themselves differently when freezing. Even in the early universe, perfect symmetry should mean no variation, yet galaxies, stars, and planets formed. This paradox appears in quantum mechanics, where particles exist in superpositions but choose an outcome when observed. It also applies to chaos theory, where tiny fluctuations, even quantum ones, create large-scale changes. The paradox raises a deep question. Does randomness exist, or are hidden factors breaking symmetry in ways we don't yet understand? The Infinite Monkey Paradox. Imagine an immortal monkey randomly pressing keys on a typewriter for eternity. Mathematically, at some point, it should type out every possible text, including Shakespeare's complete works. This seems absurd. The chances of typing just one correct sentence are astronomically small, so how could the entire play ever appear? The paradox is that in an infinite time frame, even impossibly rare events become inevitable. The paradox highlights the difference between practical impossibility and theoretical certainty. Just because something is guaranteed in infinity doesn't mean it's likely within a reasonable time span. This paradox appears in discussions of randomness and order. In quantum physics, particles fluctuate randomly, yet they sometimes form patterns. It also applies to evolution. Life may seem too complex to happen randomly, but given billions of years, even improbable events can occur. It teaches us a strange truth. Given infinite chances, even the impossible must happen eventually. The Popper's Paradox of Tolerance. Karl Popper's Paradox of Tolerance asks, should a tolerant society tolerate intolerance? If a society is completely tolerant, it allows intolerant groups to grow. If intolerant groups grow, they can destroy tolerance itself. Therefore, to protect tolerance, society must be intolerant of intolerance. This creates a contradiction. How can a tolerant society justify being intolerant? If it bans certain ideas, it starts resembling the very intolerance it opposes. But if it allows them, it risks self-destruction. This paradox is deeply relevant in politics and free speech debates. Should we allow hate speech in a free society? If we ban it, are we still free? If we allow it, do we risk eroding freedom altogether? Popper argued that unlimited tolerance leads to its own demise. A truly tolerant society, he claimed, must defend itself against intolerance. It forces us to ask, is there such a thing as too much freedom? The paradox of free will. Do we truly make choices, or is everything predetermined? The paradox of free will arises because, if everything follows cause and effect, then our thoughts and actions are just the result of prior causes, so free will is an illusion. If our choices aren't caused by anything, then they're random, which also doesn't sound like free will. Either way, true free will seems impossible. If we are fully determined, then our decisions were inevitable. But if decisions aren't determined by anything, then they're just chaos. This paradox appears in philosophy, neuroscience, and physics. Studies show the brain decides before we consciously realize it. Does that mean choice is just an illusion of the mind catching up to pre-made decisions? Some propose compatibilism, the idea that free will and determinism can coexist. Maybe free will isn't about avoiding causality, but about acting according to one's nature without coercion. The paradox makes us question whether we control our actions, or if we are just watching them happen, the temporal paradox of observation. This paradox asks, does the act of observing something change its past? In quantum mechanics, experiments show that the way we measure particles changes their behaviour, even after they've already travelled. The delayed choice experiment suggests that whether a photon acts like a wave or a particle depends on a decision made after it has passed through a setup. This means that future measurements seem to be affecting the past. How is that possible? This paradox suggests that reality isn't as fixed as we assume. In quantum mechanics, events may not be determined until they are observed, meaning the past may not be real until we look at it. The paradox raises unsettling questions about time, causality, and consciousness. If measurement can rewrite history at a quantum level, does reality even exist when unobserved? It challenges everything we think we know about time and existence. The Thomson's lamp paradox. This paradox involves a lamp that is turned on and off in an infinite sequence of decreasing time intervals. At 1 minute, turn the lamp on. At 1.5 minutes, turn it off. At 1.75 minutes, turn it back on. At 1.875 minutes, turn it off again. This continues indefinitely, meaning that by the 2-minute mark, the lamp has been switched an infinite number of times. The paradox is, what is the final state of the lamp at exactly 2 minutes? If the pattern continues forever, there is no last switch. So how do we decide if the lamp is on or off? If it's on, what made it stay on instead of off? If it's off, why didn't it stay on? This paradox exposes the problems of applying infinite logic to finite time. It resembles Zeno's paradoxes, questioning whether motion and time can be divided infinitely. It suggests that at certain limits, logic breaks down. Some questions may not have definite answers. The Fitch's Paradox of Knowability. Fitch's paradox challenges the idea that all truths are knowable. It starts with a simple assumption. If something is true, then in principle it can be known. But if we assume that all truths are knowable, this leads to a contradiction. Consider an unknown truth, P. For example, there is a planet beyond our observable universe. If P is knowable, then someone must eventually know it. But if no one can ever know P, then P is true, but unknowable, contradicting the original assumption. This paradox suggests that some truths might be permanently unknowable, even in principle. It raises deep questions about the limits of knowledge. Are there facts about the universe that we can never access? Is human knowledge fundamentally incomplete? It connects to Gödel's incompleteness theorem, which shows that some truths exist but can never be proven. This paradox forces us to rethink, can everything that is true be discovered? Or are some truths lost forever? The Stochastic Paradox. The Stochastic Paradox challenges how we interpret randomness and probability. It shows that events that seem impossible can still be expected to occur. Example: suppose you play a lottery with 1 million tickets every day for the rest of your life. The odds of winning each day are nearly zero, but over a lifetime of entries, it becomes highly likely that you'll win at least once. This paradox appears in real life. Rare disasters, earthquakes, pandemics, seem impossible on any given day, but across long timescales they are inevitable. Stock market crashes are unpredictable, but history shows they always occur eventually. Evolution operates over vast time periods. Random genetic mutations may seem unlikely in the short term, yet they drive life's development. The paradox reveals a key insight. Low probability does not mean never. Even events that seem impossible must happen given enough chances. It's a reminder that in a world of randomness, the rare is not as rare as it seems. The non-transitive dice paradox. In most games, if A is better than B and B is better than C, then A should be better than C. But in the non-transitive dice paradox, this isn't true. Consider 3 specially designed dice. Die A beats. Die B most of the time. Die B beats. Die C most of the time. But surprisingly, die C beats die A most of the time. This creates a cycle where no die is truly the best. This paradox appears in real-world decisions. Politics. A candidate can beat another in direct comparison, but lose in a 3-way election. Sports. Team A beats Team B beats Team C, but Team C beats Team A. Evolution. Some species dominate others, but no single one is best overall. It teaches us that ranking isn't always straightforward. What's better depends on context, and sometimes there is no absolute best. The paradox of the surprise birthday. Imagine your friends tell you, "We are throwing you a surprise birthday party next week, but you won't know the day until it happens." You start reasoning. If they wait until the last day, I'll know in advance, so it can't be that day. If the last day is ruled out, the second to last day also becomes predictable. Applying this logic, you rule out every day, concluding that no surprise party is possible. But when the party actually happens, you're genuinely surprised. This paradox is similar to the unexpected hanging paradox. It shows how logical deduction can sometimes fail in the real world. It applies in various scenarios. Psychology. People can overthink surprises, yet still be caught off guard. AI and decision-making. Machines that try to predict human behaviour can fail when people act irrationally. The paradox highlights the limits of rational thinking. Sometimes surprises remain surprises, no matter how much we try to predict them. The causal loop paradox. The causal loop paradox occurs when an event is both the cause and the effect of itself, forming a closed time loop with no clear origin. Example: a scientist invents a time machine and goes back in time. In the past, they give their younger self the blueprints for the time machine. The younger self builds the machine using the blueprints and later goes back in time to repeat the cycle. But where did the original idea for the time machine come from? It was never created. It simply always existed in the loop. This paradox appears in many time travel stories, e.g., a person going back to teach Shakespeare how to write his plays. It violates the principle of causality. Events normally have causes, but here, the event exists without an origin. Physicists debate whether causal loops could exist. Some theories suggest they are consistent with the laws of physics, while others argue they create contradictions that make them impossible. It raises deep questions about time. Can something exist without ever being created? The lazy paradox. The lazy paradox, or fatalist's paradox, argues that if the future is already determined, then actions in the present don't matter. Example: suppose your fate is already decided. You will pass or fail an exam regardless of how much you study. If you are destined to pass, you don't need to study. If you are destined to fail, studying won't help. Therefore, why study at all? The paradox highlights a contradiction in determinism. If fate is fixed, effort seems pointless. But in reality, our choices influence outcomes. They just might be part of the fate we think is unavoidable. It also appears in religion and philosophy, where debates exist about predestination versus free will. If everything is predetermined, does responsibility for our actions still exist? The resolution is that knowing the future, or believing it's fixed, doesn't mean effort is meaningless, because actions are still part of the causal chain leading to an outcome. It forces us to reconsider. If the future is set, do we still have free will? The immortal amoeba paradox. This paradox challenges how we think about infinity and personal identity. Imagine an immortal amoeba that splits into two identical copies every day. Each copy is indistinguishable from the original. If this continues indefinitely, then trillions of amoebas will exist in the future. But if none ever die, which one is the original? At what point does the original amoeba stop existing? If every copy is a perfect duplicate, then is there even an original anymore? This paradox appears in philosophy when discussing cloning, identity, and consciousness. If you were copied perfectly, is the copy still you? If you are gradually replaced with identical parts, at what point do you stop being yourself? It raises deep questions about identity over time. Are we the same person throughout our lives? Or do we constantly become new versions of ourselves? The Grandfather Paradox. The Grandfather Paradox is one of the most famous time travel paradoxes. Imagine you go back in time and accidentally prevent your grandfather from meeting your grandmother. If he never meets her, your parent is never born. If your parent is never born, you never exist. But if you never exist, you couldn't have travelled back in time to change the past. This paradox creates a logical contradiction. Your actions erase the conditions that allowed you to make those actions in the first place. Possible resolutions. Time protects itself. You can't change the past, only fulfill it. Parallel timelines. Your actions create a new timeline, separate from your original. Reality collapses. The paradox makes time travel impossible. This paradox raises deep questions about causality, fate, and free will. If time travel were possible, would the past be fixed, or could we change it? It challenges how we think about time. Is the past set in stone, or can it be rewritten? The Achilles and the Tortoise Paradox. This paradox comes from Zeno's paradoxes of motion, questioning whether movement is even possible. Achilles, a fast runner, gives a slow tortoise a head start in a race. Achilles runs after it, but by the time he reaches where the tortoise was, the tortoise has moved forward a little. Achilles reaches the new position, but again, the tortoise has moved forward slightly. This continues infinitely. Achilles is always closing the gap, but never quite catches up. Logically, this suggests Achilles can never pass the tortoise, even though in reality, he obviously does. The paradox comes from dividing space and time into infinite small steps. Mathematicians solved it using calculus, showing that the infinite steps converge to a finite distance. It highlights a fundamental question in physics and math. Is reality continuous or made of discrete steps? It also suggests that our intuition about infinity doesn't always match reality. The Buridan's-Ass Paradox. Buridan's-Ass is a paradox about decision-making. It describes a hypothetical donkey placed exactly between two identical piles of hay. The donkey is perfectly rational and wants to choose the better pile, but since both are equal, it has no logical reason to pick one over the other. The paradox is, what happens? If the donkey can't decide, it starves to death. But that's absurd. Clearly it should just pick one. The paradox challenges the idea that rational decision-making always works. If logic alone dictates choices, can indecision become fatal? It also applies to AI and economics. If an algorithm must choose between equal options, does it freeze? A possible resolution is that real decisions include hidden factors. Tiny differences, instincts, or randomness might tip the balance. But the paradox forces us to question: do we always make choices logically, or is some level of irrationality necessary for survival? The Eternal Recurrence Paradox. Eternal recurrence is a paradox from Nietzsche's philosophy and physics. It suggests that time might be cyclical, meaning that everything you do will happen again and again, forever. Imagine the universe collapses and restarts endlessly. Every event, every thought, every mistake, you will relive it exactly the same, an infinite number of times. The paradox is psychological. If everything repeats, does free will matter? Would you change how you live if you knew you had to relive every moment eternally? Modern physics has theories about cyclical time, e.g. the Big Bounce model. But even if reality isn't truly repeating, the paradox forces us to reflect on whether we live meaningfully if our actions echo forever. The Crow Paradox. The Crow Paradox, related to Hempel's Paradox, Raven's Paradox, questions what counts as scientific evidence. The rule: all crows are black. To prove this, we should examine crows, but logically this also means anything that is not black is not a crow. So if we observe a green apple, it technically confirms the statement, because it isn't a black crow, but this feels absurd. The paradox questions how we gather knowledge. Should indirect evidence count? Does logic always align with common sense? In science and machine learning, this matters. If we only look for confirming evidence, do we risk ignoring real counterexamples? It forces us to rethink what really proves something, and what just seems like it does. The Quantum Suicide Paradox. The Quantum Suicide Paradox is a thought experiment based on quantum mechanics and the many worlds interpretation, MWI. Imagine a physicist in a deadly quantum experiment. A machine measures a quantum particle's state. If it's spin up, the physicist survives. If it's spin down, the physicist is instantly killed. If MWI is correct, the universe splits at each measurement. In one universe, the physicist dies. In another, they survive. From their perspective, they always experience survival, because in any reality where they are aware, they are still alive. This suggests a person should never experience death, because there will always be a surviving version. This paradox raises huge philosophical questions. Does consciousness jump between realities where survival continues? If this is true, is everyone effectively immortal in their own timeline? Some see it as proof that we misunderstand death and probability. Others think it's pure speculation, but it challenges everything we assume about consciousness and existence. The problem of induction paradox. This paradox, proposed by David Hume, questions how we justify knowledge from experience. Example: every day, the sun rises. We assume it will rise tomorrow based on past observations. But logically, past events don't guarantee future ones. This is the problem of induction. Science, logic, and everyday life rely on patterns, but we have no absolute proof that patterns will continue. Just because something has always happened doesn't mean it must happen again. This paradox is at the heart of science and skepticism. It raises the question, are our beliefs just habits? If so, how do we justify anything beyond past experience? A modern response is Bayesian reasoning, where beliefs update with probability. But the paradox still lingers. Do we know things, or just assume they will keep working? The infinite sphere paradox. The infinite sphere paradox comes from set theory and infinity. It asks, how big is infinity? Imagine two spheres, a small sphere, a large sphere. Now map every point on the small sphere to a point on the large sphere. Surprisingly, it's possible to make a perfect one-to-one correspondence between them. Even though the large sphere is infinitely bigger, the paradox is that the small sphere and large sphere have the same number of points despite vastly different sizes. This paradox reveals a counterintuitive truth about infinity. Size doesn't matter when dealing with infinite sets. Its importance in cosmology. If the universe is infinite, does it contain an infinite number of identical copies of Earth? It also appears in mathematics, where infinite sets behave differently from finite ones. It challenges how we think about space, size, and reality. Can something be infinitely big, yet still match something infinitely small? The missing dollar paradox. This classic paradox plays with numbers in a misleading way. 3 people share a hotel room for $30. They each pay $10. The hotel clerk later realizes the room only costs $25, so he gives the bellboy $5 to return. The bellboy keeps $2 and gives $1 back to each guest. Now each guest has paid $9, $10. $10, meaning they paid a total of $27. The bellboy kept $2, making $29. But wait, where's the missing $1 from the original $30? The trick here is a false equation. The $27 already includes the bellboy's $2. Adding it again is a mistake. It's a lesson in how misdirection in math can create fake paradoxes. It's used in education to show why careful accounting matters, especially in finance. The secretary problem paradox. The secretary problem is a paradox in decision-making and probability. It asks, how do you hire the best secretary when candidates appear one by one, and once rejected, they're gone forever? If you wait too long, the best candidate might be gone, but if you choose too soon, you might miss someone better. Mathematicians found an optimal strategy. Review 37% of candidates without choosing. After that, pick the first one who is better than all previous ones. This gives about a 37% chance of selecting the best. The paradox is that random selection seems better than careful judgment. The strategy appears in dating, hiring, and investments. It suggests there's an optimal point to stop searching and commit. It forces us to rethink, is waiting always better, or should we take the best option early? The Jevons Paradox. Jevons Paradox states that improving efficiency doesn't always reduce consumption. Sometimes it increases it. Example: a new fuel-efficient engine reduces gasoline use per mile. But since driving is now cheaper, people drive more, increasing total fuel consumption. This paradox appears in energy policy. Better appliances lower energy costs, but people use them more. Water use. Efficient irrigation saves water per acre, but encourages more farming, using more water overall. Technology. Faster internet lowers data costs, leading to more data consumption. It challenges the belief that efficiency equals conservation. Instead, it suggests that saving resources often leads to higher demand, making conservation harder. Jevons Paradox is a warning. Solving problems sometimes makes them worse. The Arrow's impossibility theorem. Arrow's theorem is a paradox in voting systems. It proves that no perfect voting system exists when choosing among 3 or more options. It states that any fair voting method must satisfy 3 conditions. Unanimity. If everyone prefers A over B, A should win. Independence. The choice between A and B shouldn't be affected by a third option, C. No dictatorship. No single voter should always decide the outcome. The paradox is, no system can meet all three conditions at once. Majority rule can be unfair in three-way votes. Ranking systems, like ranked choice voting, can still produce illogical results. Tiebreaker methods introduce bias. This means that democracy itself has mathematical flaws. No voting method is entirely fair. The paradox forces us to rethink elections, governance, and fairness. Is there even such a thing as a perfect democracy? The trolley problem paradox. The trolley problem is one of the most famous paradoxes in ethics and moral philosophy. Imagine a runaway trolley heading toward 5 people tied to the tracks. You stand next to a lever that can divert the trolley onto another track. But on this second track, there is one person. Do you pull the lever and sacrifice one life to save 5? At first, the choice seems obvious. Saving 5 lives is better than losing them all. But the paradox emerges when we start questioning the morality of actively causing harm. If you pull the lever, you intentionally kill someone, even if your goal is to minimize total harm. But if you do nothing, 5 people die, not by your hand, but as a result of inaction. Which is worse? Variations of the problem make it even more complicated. What if the one person is a loved one? What if the 5 people are criminals? What if you had to physically push a person onto the tracks instead of pulling a lever? The deeper problem is that ethics is not always simple. Can morality be reduced to a math equation? Or does intent matter more than outcome? The paradox plays a role in artificial intelligence. Self-driving cars, for example, may need to make real-world decisions about who to save in unavoidable accidents. It also appears in military strategy, medicine, and everyday moral dilemmas. Ultimately, the trolley problem forces us to confront the uncomfortable reality that many moral choices involve sacrifice, and that no answer is truly satisfying. The Abilene Paradox. The Abilene Paradox is a psychological paradox about decision-making in groups. It describes situations where a group collectively decides on an option that no individual actually wants, simply because everyone assumes the others want it. Imagine a family on a hot summer day. One person suggests taking a long drive to Abilene for dinner. No one really wants to go, but they all agree, thinking the others are in favour. After a long, miserable trip, they realise none of them actually wanted to go. They all just went along with it to avoid disagreement. This paradox highlights how poor communication and social pressure can lead to irrational group decisions. It happens in business, politics, and personal relationships. People stay silent, assuming others support an idea, when in reality everyone is privately against it. The paradox is closely related to groupthink, where individuals suppress their own opinions to conform. It's dangerous because it prevents honest discussion and leads to bad decisions. Companies make bad investments, governments pursue unpopular policies, and teams waste time on projects that no one believes in, all because people are afraid to speak up. The lesson of the Abilene Paradox is simple but powerful. We should never assume that silence equals agreement. Honest discussion is crucial for making better decisions. The Sorites Paradox. The Sorites Paradox, also called the paradox of the heap, questions the nature of vague definitions. It begins with a simple idea. If you take a single grain of sand, it is not a heap. If you add one more grain, it is still not a heap. But if you keep adding grains, at some point it becomes a heap. But where exactly does the change happen? If one grain doesn't make a difference, then adding another shouldn't either. This logic seems to suggest that no amount of sand ever becomes a heap, which is clearly absurd. But if we try to define a specific cutoff, say 1,000 grains, then what about 999 grains? The paradox shows that language struggles to deal with gradual change. This applies to many real-world problems. When does a fetus become a person? When does a balding man become bald? When does poverty turn into wealth? These issues are difficult because vague concepts like heap, bald, and rich don't have precise boundaries. The paradox challenges how we define categories. Some philosophers argue that vagueness is an unavoidable flaw in language, while others propose using probability or logic to handle borderline cases. Either way, it shows that many debates arise simply because we lack clear definitions. The Liar's Paradox. The Liar's Paradox is one of the most famous self-referential paradoxes in logic. It involves a simple statement. This statement is false. If the statement is true, then what it says must be correct, meaning it is false. But if it is false, then what it says must be incorrect, meaning it is actually true. The statement is trapped in an endless logical loop. This paradox breaks traditional logic, which assumes statements must be either true or false, but not both. It challenges the foundation of mathematics, philosophy, and even artificial intelligence. If a machine were programmed to evaluate statements, the liar's paradox would trap it in a loop. Variations of the paradox appear in real life. Politicians sometimes claim, "I always lie," which creates the same contradiction. Even in programming, recursive loops can cause infinite crashes. In logic, some have proposed solutions like three-valued logic, where statements can be true, false, or undefined. Others argue that self-referential statements are meaningless, like dividing by zero. The paradox raises deep questions. Can truth always be defined, or are there limits to what we can logically prove? The Hilbert's Hotel Paradox. Hilbert's Hotel is a paradox about infinity that exposes how counterintuitive infinite sets can be. Imagine a hotel with an infinite number of rooms, all of which are occupied. Now suppose a new guest arrives. Since all rooms are full, it seems impossible to accommodate them. But there's a trick. Move the guest in room 1 to room 2. Move the guest in room 2 to room 3. Move the guest in room 3 to room 4, and so on. Now room 1 is empty, and the new guest can check in, despite the fact that the hotel was already full. Even stranger, what if infinite new guests arrive? By shifting everyone to room 2n, double their room number, we free up all odd-numbered rooms, creating infinite empty spaces in an already full hotel. This paradox reveals that infinity doesn't behave like regular numbers. In finite hotels, full means full, but with infinity, you can always make room. It challenges our understanding of space, numbers, and logic. Hilbert's Hotel has implications in set theory, physics, and cosmology. It suggests that the universe itself might behave like an infinite hotel, always full, yet somehow never out of space. It's a mind-bending lesson in how infinity is stranger than we ever imagined. The Simultaneity Paradox. The Simultaneity Paradox arises from Einstein's theory of relativity, which states that simultaneity is not absolute. What is simultaneous for one observer may not be for another. Imagine a train moving at near light speed. Two lightning bolts strike the front and back of the train at the same time, as seen by a person standing on the platform. However, for a person inside the train, the lightning at the front seems to strike later than the one at the back, because the train is moving toward the front strike and away from the back strike. Who is correct? Both are. According to relativity, there is no universal now. Time depends on the observer's motion. This paradox fundamentally challenges our everyday intuition of time, showing that simultaneity is not absolute but relative to motion. This isn't just theoretical. GPS satellites must correct for time differences caused by their speed relative to Earth. The paradox forces us to rethink our perception of time itself. Is time just an illusion shaped by movement? The Kafka's toxin paradox. Kafka's toxin paradox is a paradox of intention and rationality. Imagine a billionaire offers you $1 million if, by midnight, you can genuinely intend to drink a poison. The poison won't kill you, just make you sick for a day. But here's the trick. You get paid based on intent alone, not whether you actually drink it. By midnight, you must honestly believe you'll drink it. But once the money is transferred, there's no reason to drink it anymore. The paradox is, can you force yourself to intend something while knowing you won't follow through? If you can, you get the money. But if you think logically, you realise there's no reason to drink it, so you won't truly intend to drink it. This paradox exposes a conflict between commitment and rational action. It appears in business, politics, and even personal life. How do you make credible promises when future incentives change? The deeper issue is, can rationality be self-defeating? The knowledge paradox. The knowledge paradox questions whether we can ever truly know everything. It's based on a simple idea. If you know something, you must be aware of it. If you are unaware of something, then you don't know it. But what if you don't know what you don't know? This leads to a contradiction. Can something be true and knowable, yet never actually known? It appears in science and philosophy. Gödel's incompleteness theorem suggests that some truths cannot be proven. Fitch's paradox of knowability shows that if everything were knowable, paradoxically, some truths must remain unknown. The paradox forces us to confront our intellectual limitations. Is knowledge ever truly complete? Or is the unknown an unavoidable part of existence? The exponential growth paradox. The exponential growth paradox shows how slow, unnoticed changes can suddenly become catastrophic. Imagine a pond where lily pads double in size every day. If it takes 30 days to cover the pond, on what day is it only half covered? Day 29. This means that even if the pond looks mostly empty for weeks, it explodes into full coverage in just a few days. This paradox appears in finance, population growth, and resource depletion. Debt grows slowly at first, then spirals out of control. Technology evolves gradually, then suddenly advances at an astonishing rate. Ecosystem collapse happens after decades of small changes. It warns us that exponential change is deceptive. By the time we notice, it may be too late. The lesson: we underestimate slow-growing problems because they seem small, until they aren't. The noise paradox. The noise paradox questions whether perfect silence is even possible. Imagine a completely soundproof room. Now ask: if no one hears a sound, does it exist? If absolute silence is real, how do we detect it? The paradox is that perfect silence is an illusion. Even in a vacuum, particles vibrate. Even in deep space, background radiation hums. Even in our minds, we hear internal noise. It applies to physics, neuroscience, and philosophy. Quantum physics suggests there is always energy fluctuating in space. In human perception, silence makes us more aware of tiny sounds, like our own breathing. In philosophy, it asks, can the absence of something be a thing itself? The noise paradox teaches us that true emptiness doesn't exist. Even in silence, something is always happening. The Baron-Munchausen trilemma. The Munchausen trilemma is a paradox in epistemology, the study of knowledge, that questions whether absolute certainty is possible. It states that any attempt to prove a truth ultimately leads to one of three unsatisfying outcomes: infinite regress. Every proof requires another proof, which requires another proof, leading to an endless chain of justification. Circular reasoning. A statement is used to prove itself, which is logically meaningless. Dogmatism. The reasoning stops at an unquestionable assumption, which is just blind faith rather than proof. The paradox is named after Baron Munchausen, a fictional character who supposedly pulled himself out of a swamp by tugging on his own hair. Just as we try to prove truth by relying on assumptions we can't justify. It suggests that absolute knowledge is impossible. Every belief is ultimately based on something unprovable. This paradox challenges science, logic, and philosophy. Is knowledge ever truly solid, or is it always built on assumptions? The best we can do may be choosing the most useful assumptions, rather than proving everything from nothing. The bald man paradox. The bald man paradox, also called the Sorites Paradox, is about vague definitions. Imagine a man with a full head of hair. If you pluck one hair, he is still not bald. But if you keep removing hairs, at some point he becomes bald. The paradox is, where is the exact point when he becomes bald? If one hair doesn't make a difference, then it seems no number of hairs should. But clearly, a man with 0 hair is bald. This paradox applies to many real-world situations. When does a person go from rich to poor? When does a fetus become a person? When does a pile of sand become a heap? The issue is that natural language lacks clear boundaries for gradual changes. Philosophers suggest solutions like fuzzy logic, where truth is not black or white but exists on a spectrum. The paradox forces us to ask, are vague concepts always flawed, or do we need new ways to define them? The Ellsberg Paradox. The Ellsberg Paradox challenges the idea that humans make decisions rationally based on probability. It shows that people often prefer known risks over unknown risks, even when that leads to irrational choices. Imagine 2 urns filled with red and black balls. Urn A contains exactly 50 red and 50 black balls. Urn B contains 100 balls, but in an unknown ratio of red to black. Now you must bet on drawing a red ball from one of the urns. Most people choose urn A because they know the exact odds, 50%. But logically, urn B could have a better ratio, and you have no reason to assume it doesn't. The paradox shows that people have an irrational fear of uncertainty, ambiguity aversion. Instead of acting purely on logic, we prefer situations where the risk is clear, even if it's not optimal. This paradox applies to finance, business, and everyday life. People avoid investments they don't understand, reject medical treatments because of unknown side effects, and fear unknown dangers more than proven but risky ones. It suggests that our brains are wired to avoid uncertainty, even when it's the better choice. The Moravec's Paradox. Moravec's paradox is a surprising observation about artificial intelligence, AI. Hard tasks for humans are easy for AI, but easy tasks for humans are hard for AI. For example, AI can beat humans in chess, do complex math, and process vast amounts of data better than any person. But AI struggles to walk, recognize objects, or understand emotions, tasks that even a toddler can do effortlessly. This paradox happens because high-level reasoning, math logic, is a recent human development, while basic movement and perception evolved over millions of years. Our brains are highly optimized for survival-based tasks like recognizing faces, grasping objects, or running. But logical thinking is a newer skill that AI finds easier to replicate. The paradox highlights the challenges in robotics, automation, and AI development. It suggests that true artificial intelligence won't be just about thinking. It must master intuition, movement, and perception, just like humans. The self-defeating prediction paradox. The self-defeating prediction paradox describes a situation where predicting an event causes it to become false. Example: a bank is predicted to collapse next week. Customers panic and withdraw their money before the collapse happens. The bank collapses sooner than predicted, meaning the prediction was wrong. This paradox appears in economics, politics, and psychology. If a traffic jam is predicted, people avoid the road, so the jam never happens. If a war is predicted, countries prepare, possibly preventing the war. If AI predicts stock prices will drop, investors sell early, causing the drop to happen earlier than expected. It highlights the power of self-fulfilling and self-defeating prophecies. Sometimes, knowing the future can change it. The paradox raises the question: how much of the world is shaped by the predictions we believe? The Buttered Cap Paradox. The Buttered Cap Paradox is a humorous thought experiment that combines 2 common paradoxes: Murphy's law of buttered toast. Toast always lands butter side down. The cat writing reflex. Cats always land on their feet. Now suppose you butter the back of a cat and drop it. What happens? If the buttered toast rule holds, the cat should land butter side down. If the cat's reflex holds, it should land on its feet. The paradox suggests that the cat should hover in midair, spinning endlessly, because neither rule can be violated. Obviously, this is a joke, but it touches on a real philosophical idea. What happens when two fundamental laws contradict each other? Similar conflicts appear in physics, logic, and AI. What happens when a robot is programmed to always obey two rules that sometimes conflict? While not meant to be taken seriously, the paradox plays with our expectations about rules and reality, making us rethink how logic interacts with absurdity. The dollar auction paradox. The dollar auction paradox is a game theory paradox that shows how rational decisions can lead to irrational outcomes. A simple game. A $1 bill is auctioned to the highest bidder. Bidding starts at 1 cent and increases in small steps. The twist. Both the highest bidder and the second highest bidder must pay their final bid. But only the highest bidder wins the dollar. At first it seems harmless, but as the price nears $1, players don't want to lose their money and keep bidding. When the bidding reaches $1, the second highest bidder has already spent 99 cents, so they bid $1.01 to avoid a total loss. Now the other player, who has spent $1, bids $1.02 to avoid wasting $1, and so on. The paradox is that players end up paying more than $1 for a $1 bill, a completely irrational outcome that resulted from making logical decisions at each step. This paradox appears in real life. Wars. Countries escalate conflicts to avoid losing their prior investments. Business rivalries. Companies spend billions on marketing wars that don't benefit them. Gambling. Players chase losses to win back money, only digging deeper. It teaches a harsh lesson. Knowing when to stop is often more valuable than winning. The boy or girl paradox. The boy or girl paradox is a probability puzzle that confuses intuition. Scenario 1. A family has 2 children. You ask, at least one is a boy. What is the probability that the other is also a boy? At first you might think 50%, but the correct answer is 1/3. Why the possible child combinations are boy-boy, boy-girl, girl-boy, girl-girl, excluded because we know at least one is a boy. That leaves 3 possibilities, only one of which is boy-boy, meaning the probability is 1/3, not 1/2. Scenario 2. If you instead ask, this family has a son named John, what's the probability the other child is a boy? Swing. Now the probability is 50%. Why? Because naming a specific child eliminates the girl-boy and boy-girl cases, leaving just boy-boy or boy-girl. This paradox teaches that the way a question is framed can completely change the probability outcome, a key issue in statistics, science, and decision-making. The two envelopes paradox. The two envelopes paradox is a decision-making puzzle about probability and expectation. Imagine 2 envelopes, each containing some amount of money. You choose one and open it. Now you're told that the other envelope has either half or double the amount you see. Should you switch? At first, switching seems pointless. There's a 50% chance of gaining or losing. But mathematically, if you have X dollars, the other envelope has either X dollars divided by 2 or 2 times X dollars. The expected value is 0.5 times X dollars divided by 2 plus 0.5 times 2 times X dollars. $2 times X equals $1.25 times X. Since the expected value is greater than what you hold, it seems you should always switch. But then if you switch and reevaluate, the logic applies again, suggesting an infinite loop of switching. The paradox arises because it assumes the 2 envelopes are chosen randomly, which isn't always true in real setups. It highlights problems in decision theory and probability, showing that even seemingly simple choices can create logical contradictions. The sleeping barber paradox. The sleeping barber paradox is a logic puzzle that exposes a flaw in self-referential rules, especially in computer science and set theory. Imagine a small town with one barber. The barber follows a simple rule. I shave everyone who does not shave themselves and no one else. Now ask, who shaves the barber? If he shaves himself, he violates the rule, because he only shaves those who don't shave themselves. If he doesn't shave himself, then according to the rule, he should shave himself. This paradox is similar to Russell's paradox, which questions whether a set of all sets that don't contain themselves can exist. In computer science, it reveals why self-referential logic can break a system. Programs must avoid rules that create infinite loops or contradictions, or they'll crash. It's also a philosophical problem. Can language and rules ever fully describe reality without contradictions? The sleeping barber suggests that some systems create paradoxes simply by how they are defined. The overfitting paradox. The overfitting paradox is a problem in machine learning and statistics, where a model becomes too good at learning details from a dataset, so good that it fails in the real world. Imagine teaching a robot to identify cats. If it memorizes every tiny detail of the training photos, it might learn that cats always appear in sunny backgrounds. Now, when you show it a cat in the rain, it fails to recognize it. Instead of learning general patterns, it overfits to specific examples, which actually makes it worse at recognizing real-world cases. The paradox is that trying to be perfect makes the model useless. Instead of true learning, the model is just memorizing noise. This problem appears beyond AI hiring. If a company only hires based on past perfect employees, they may miss great candidates who don't fit an exact pattern. Science. If researchers overfit data to a theory, they might ignore broader patterns. Life. If we only trust ideas that match past experiences, we may fail to adapt to new situations. The lesson. Seeking perfection can lead to worse decisions. Simplicity and adaptability often work better than overcomplication. Olbers Paradox. Olbers Paradox asks a simple but profound question. Why is the night sky dark if the universe is infinite? If the universe has infinite stars, then no matter where we look, a star should fill every part of the sky. The night sky should be as bright as the surface of the sun. But it isn't. Why? Solutions to the paradox include: the universe isn't infinitely old. Light from distant stars hasn't reached us yet. The universe is expanding. Distant galaxies are moving away, shifting their light into the infrared, redshift, making them invisible to the human eye. Dust absorbs light. Interstellar dust blocks some starlight, though this alone doesn't fully solve the paradox. This paradox helped scientists realize that the universe has a beginning, Big Bang, and is still evolving. It challenges our intuition. If something should be true logically but isn't observed, then our assumptions might be wrong. Olbers' paradox teaches us that even obvious questions can lead to revolutionary discoveries about the nature of reality. The confirmation bias paradox. The confirmation bias paradox is a self-reinforcing loop where seeking truth actually makes people more wrong. People naturally look for evidence that supports what they already believe, rather than challenging their views. If someone believes in conspiracy theories, they only seek sources that confirm them. Over time, their belief grows stronger, not because it's correct, but because they filter out contradictory evidence. The paradox is, the more you confirm a belief, the less likely you are to ever question it. Even when new evidence proves you wrong, you may ignore it, making you more confident in your mistake. This paradox appears in politics. People consume media that supports their side, reinforcing extreme views. Science. If a scientist only publishes data that confirms a theory, the truth is distorted. Personal life. If you assume someone dislikes you, you may only notice negative actions, ignoring positive ones. It's dangerous because rational people can still fall into it, not because they're irrational, but because they seek patterns that fit their beliefs. The only way to escape? Actively seek disconfirming evidence, a skill that requires humility and critical thinking. The Thoughtcrime Paradox. The Thoughtcrime Paradox comes from George Orwell's 1984, where even thinking a forbidden idea is considered a crime. The paradox is, if thought itself is punishable, how do you prove someone has committed a crime without mind reading? If people fear punishment for thinking, they self-censor. But can you punish something that never manifests? This paradox exists in real-world issues. Totalitarian states criminalize certain beliefs, but how can they know who thinks what? Pre-crime technology, predicting future criminals, assumes people will act based on thoughts, but many thoughts never lead to actions. Social media outrage. People are cancelled for private thoughts or old posts, assuming thought formats crime. The paradox raises serious ethical concerns. Should intention be punishable, or only actions? Does preventing dangerous ideas protect society, or does it create an oppressive system? It challenges the boundary between freedom of thought and responsibility. Should people be held accountable for what they think, even if they never act on it? The Observer's Paradox. The Observer's Paradox. The Observer's Paradox states that the act of observing something changes it, so we can never truly study something without influencing it. Example: if a researcher wants to study how people naturally talk, but people know they're being recorded, they speak differently. This means the natural behaviour they want to study disappears the moment they observe it. This paradox appears everywhere. Quantum mechanics. In the famous double-slit experiment, particles behave differently when measured, suggesting observation affects reality itself. Psychology. People act more polite, cautious, or dishonest when they know they're being watched. Social studies. Surveys are unreliable because people modify answers to appear socially acceptable. It's a problem because it means pure, unbiased observation may be impossible. If observing something changes it, then how can we ever be sure what's real? One solution is to reduce awareness of observation, but this raises ethical issues. Is it ever okay to observe people without their knowledge? The paradox forces us to ask, is reality different when we aren't looking? And if so, can we ever truly understand it? The ghostly coincidence paradox. The ghostly coincidence paradox refers to eerie coincidences that seem so improbable that they feel supernatural, yet they are mathematically inevitable given enough time and events. For example, imagine thinking about an old friend you haven't seen in years, and then they suddenly call you the next day. This feels like a mystical connection, but mathematically, in a world with billions of people and constant events, some strange coincidences are bound to happen. The paradox is that coincidences feel too unlikely to be random, but the more time passes, the more inevitable they become. It applies to real-world phenomena like déjà vu, feeling like you've experienced something before, even when it's just a mix of memory errors and probability. Psychic predictions. Someone makes thousands of predictions, and a few come true by chance, making them seem prophetic. Strange deaths and accidents. People have died in ways eerily similar to past family members, but out of millions of deaths, some patterns will emerge. The paradox teaches us that our brains are wired to seek meaning in randomness, making us see patterns where none exist. Just because something is rare doesn't mean it has a deeper cause. It may simply be the universe playing with large numbers. The theological fatalism paradox. The theological fatalism paradox asks, if an all-knowing God already knows the future, can humans have free will? Consider this dilemma. If God knows what you will do tomorrow, then your actions are already predetermined. If they are predetermined, then you cannot change them. Your choices are an illusion. But if you truly have free will, then God cannot perfectly know the future. This paradox challenges the idea that free will and divine foreknowledge can coexist. If an omniscient being already knows your choices, then aren't they fixed in advance, making choice meaningless? Religious philosophers have attempted solutions that God sees all time at once, meaning free will exists, but only from our perspective. Foreknowledge doesn't cause events. God may know what happens, but knowledge isn't forcing the outcome. Open theism. The future is partially unknown, even to God, allowing free will to exist. The paradox forces us to question, can free will exist in a universe where the future is already written? Or are we just following a script we can't see? The evolutionary paradox of selfishness. Evolution teaches that organisms should act in their own self-interest to survive and reproduce. However, nature is full of acts of altruism, animals helping others at their own expense. This creates a paradox. Selfish creatures should outcompete altruistic ones. Yet altruism is widespread. Bees die defending the hive, penguins share food, humans donate money to strangers. If evolution favours survival and reproduction, then why do organisms sacrifice themselves for others? Shouldn't selfish genes always win? Possible explanations include kin selection. Helping relatives indirectly passes on shared genes, making altruism genetically beneficial. Reciprocal altruism. Helping others increases the chance of being helped later, making cooperation mutually beneficial. Group selection. Groups with more cooperation tend to survive better than purely selfish ones. This paradox teaches that evolution isn't just about the individual. It also favours strategies that benefit the survival of groups and social structures. It forces us to rethink, is true selflessness possible, or is altruism just another survival strategy? The uncertainty principle paradox. The uncertainty principle, discovered by Werner Heisenberg, states that the more precisely you measure a particle's position, the less precisely you can measure its momentum, and vice versa. The paradox is that reality itself seems to resist precise measurement. If you try to pinpoint where an electron is, you automatically lose information about how fast it's moving. This isn't due to instrument limitations, it's a fundamental property of nature. This paradox leads to strange consequences. Particles don't have fixed locations, they exist in probabilities. Observing reality changes reality, since measurement disturbs the system. It suggests that determinism is false. The universe isn't like a clock, but a sea of probabilities. The paradox deeply affects quantum physics, philosophy, and technology. Quantum computers rely on it. It forces us to ask, if reality is uncertain at its core, can we ever truly know anything with complete certainty? The Time Traveler's Quine Paradox. The Time Traveler's Quine Paradox is a variation of the causal loop paradox, where an object has no origin, it simply exists. Imagine a time traveller finds a rare coin on the street and keeps it. Years later, they use a time machine and accidentally drops the coin in the past, where it is later discovered by their younger self. The younger self keeps the coin and eventually travels back in time, dropping it again, completing the loop. The paradox is, where did the coin originally come from? It was never created, it simply exists in a loop forever. If it has no origin, then how did it come into existence in the first place? The coin is a causeless object, violating normal rules of reality. This paradox challenges our understanding of causality, time, and existence. Can something exist without ever being created? If so, does time travel allow for self-sustaining objects and information to exist without a source? It suggests that time loops might be possible, but they break our normal understanding of cause and effect. The Zermelo's Paradox. Zermelo's paradox is rooted in set theory, the foundation of modern mathematics. It challenges the idea of a universal set that contains all sets. Imagine a set that includes everything, including all possible sets. Now ask, does this set contain itself? If it does, it contradicts the rules of well-defined sets. If it doesn't, then it's missing something, itself. This paradox is similar to Russell's paradox, which asks whether a set of all sets that do not contain themselves should include itself. If it does, it violates its own rule. If it doesn't, then it should be included, creating a contradiction. The solution was to rebuild set theory using strict rules, Zermelo-Fraenkel set theory, preventing self-referential contradictions. However, the paradox highlights a deep issue. Even the most fundamental ideas in math can lead to logical contradictions if not carefully structured. It teaches us that infinity, self-reference and logic don't always work the way we intuitively expect. Mathematics must be carefully constructed to avoid paradoxes. The mu problem paradox. The mu problem paradox comes from Buddhist philosophy and logic, particularly in Zen koans, riddles that challenge binary thinking. In many Western logic systems, a question must have a yes or no answer, but in Zen some questions are flawed, and the correct response is neither yes nor no, but mu, meaning unask the question. Example: does a dog have Buddha nature? Answer: mu, because the question itself assumes a false premise. This paradox shows up in modern philosophy and AI. Some questions contain false assumptions, e.g., have you stopped cheating on your tests? AI trained to answer only yes/no may struggle with problems requiring a third option. The mu problem forces us to rethink how we frame problems. Instead of choosing between wrong answers, sometimes the best solution is rejecting the question itself. The island rule. Paradox. The island rule, or Foster's rule, is an evolutionary paradox. Why do big animals shrink on islands while small animals get bigger? Large animals, like elephants, evolve to be smaller because resources are limited and smaller bodies require less food. Small animals, like rodents, evolve to be bigger because fewer predators allow them to grow without risk. At first, this makes sense, but the paradox is, why do some species follow the rule while others don't? If islands limit resources, why don't all species shrink? If islands have fewer predators, why do some large animals still get smaller? For example, dwarf elephants evolved on islands, but some island species of lizards actually became larger and more aggressive. The rules are inconsistent, making predictions difficult. The paradox forces scientists to ask, are biological rules universal, or do they only apply in certain cases? The island rule suggests that evolution is complex, and while patterns exist, exceptions challenge simple explanations. The Wigner's friend paradox. The Wigner's friend paradox extends the Schrödinger's cat experiment to question whether reality itself is subjective. Imagine two scientists. Wigner's friend performs an experiment in a sealed lab. Inside, a quantum event either collapses into outcome A or B. Outside the lab, Wigner doesn't know the outcome and treats it as a superposition of both states. Here's the paradox. From the friend's view, the experiment has a definite result. Reality is fixed. From Wigner's view, the lab still exists in a quantum superposition. The result isn't real until he checks. This suggests that reality depends on the observer. What's real to one person may not exist for another until observed. Implications. Does quantum mechanics mean reality is observer-dependent? Could different people live in different versions of reality without knowing? If observation creates reality, what happens if two observers disagree on what they see? The paradox forces physicists to reconsider the nature of measurement, consciousness, and whether there is a single objective reality. The Banach-Tarski Paradox. The Banach-Tarski Paradox is one of the strangest paradoxes in mathematics. It claims you can cut a sphere into pieces and reassemble them into two identical spheres without adding any extra material. How? Take a solid sphere and break it into 5 infinitely small, precisely defined pieces. Rearrange those pieces using specific mathematical transformations. End up with 2 identical spheres, each the same size as the original. This violates common sense. How can something double in size without gaining mass? But mathematically, it works using a branch of set theory called measure theory, where some infinite sets can be rearranged in counterintuitive ways. Why does this paradox matter? It shows that infinity breaks normal rules. It challenges how we think about space and volume. In higher dimensions, splitting an object doesn't always work the way we expect. It proves that math isn't always bound by physical laws. While this can't happen in real life, atoms can't be split infinitely. It's completely possible in pure mathematics. The Banach-Tarski. Paradox teaches us that mathematics can describe realities that don't seem possible in our universe. It forces us to ask, is math a perfect description of reality, or is it something beyond it? The infinite compression paradox. The infinite compression paradox questions whether space can be divided infinitely and still contain information. Imagine a book that is infinitely compressed. Each page is half the thickness of the previous one. If you keep compressing it this way forever, the book should have an infinite number of pages, but a finite thickness. This seems impossible. How can something contain infinite parts and yet fit into a limited space? This paradox appears in physics and computing. Black holes. Information is stored on their surface, but still encodes everything inside, leading to the holographic principle. Quantum physics. Can physical states be infinitely divided, or does reality have a pixel size? Planck scale. Data compression. If information could be infinitely compressed, could we store infinite knowledge in a finite space? It forces us to question, does infinity actually exist in reality, or is it just a mathematical construct? If space can be infinitely divided, how does anything have definite size? The paradox of the infinite middle. This paradox asks, if the middle of 2 points can always be divided, does motion ever truly finish? Consider a simple task, walking across a room. You reach the halfway point first, then the next halfway point of what's left, then the next halfway point, and so on. Since there's always a smaller halfway point to reach, how do you ever arrive at your destination? Shouldn't you be stuck moving forever? This paradox is related to Zeno's paradoxes, but modern calculus resolves it. An infinite number of steps can still sum to a finite distance, just as 1/2 plus 1/4 plus 1/8 plus equals 1. However, it still raises deep questions in time, motion, and physics. Does the universe have a smallest possible step, Planck time? If space is infinitely divisible, does motion exist in a smooth flow or in jumps? It makes us wonder, is movement an illusion caused by how we perceive time? The existential risk paradox. This paradox deals with the probability of human extinction and why civilizations may overlook catastrophic risks. Logically, societies should prioritize survival threats like artificial intelligence surpassing human control, climate change becoming irreversible, a supervolcanic eruption wiping out most life. Yet paradoxically, societies rarely prepare for existential risks properly, even though extinction is the worst possible outcome. Reasons for this paradox: lack of urgency. Since extinction has never happened before, people underestimate the risk. Optimism bias. We've survived every past disaster, so we'll survive the next one. Tragedy of the commons. No single nation feels responsible for global threats. The paradox suggests that civilizations may be doomed by their own inability to take unlikely but catastrophic dangers seriously. It forces us to ask, if humans are capable of preventing our own extinction, why do we consistently ignore the biggest threats? The Schrödinger's box paradox. The Schrödinger's box paradox is a variation of Schrödinger's cat, but instead of asking about the cat, it asks, what happens if you don't open the box? If a quantum event, like radioactive decay, determines whether a cat inside lives or dies, does the cat remain in superposition forever if no one checks? If so, does reality itself remain uncertain until observed? What if no one in the entire universe ever observes the box? Would the event remain undecided for all time? The paradox suggests that observation creates reality, but this leads to absurd conclusions. If no one looks, does the event ever really happen? This has implications for the nature of reality and consciousness. Does the universe exist independently of observation? Are we collapsing reality into definite states just by looking at it? It forces us to rethink whether things exist before they are measured, or if reality is fundamentally observer-dependent. The anthropic doomsday paradox. The anthropic doomsday paradox argues that based on probability, we may be closer to the end of humanity than we think. It works like this. Suppose 100 billion humans have existed before you. If humanity lives for millions more years, the total number of humans might be trillions. But if we are near the end, the total might be only a few hundred billion, meaning you are born at a typical moment in history. If you assume you are an average human, then statistically, you are more likely to be near the end rather than the beginning of human history. This paradox challenges assumptions about the future. If we assume humanity will last forever, the odds suggest we are extraordinarily early, which seems unlikely. If we assume the end is near, it strangely aligns with probability, which is unsettling. The paradox is a warning. We may assume we have a long future ahead, but statistics suggest civilization-ending disasters are more likely than we'd like to believe. It forces us to ask, how do we know we aren't living in the final chapter of human history? The faint young sun paradox. The faint young sun paradox challenges how early Earth remained warm enough for life, despite the sun being much weaker billions of years ago. According to astrophysical models, the sun was 30% dimmer during Earth's early history. With such low energy output, Earth's surface should have been frozen solid, making the emergence of liquid water and life impossible. Yet evidence shows that oceans existed and life thrived billions of years ago. This paradox raises big questions. If the sun was weaker, what kept Earth warm enough for liquid water? Did greenhouse gases like CO2 and methane compensate for the lower sunlight? Was Earth's albedo different, absorbing more heat? Scientists have proposed solutions like a thicker atmosphere, stronger greenhouse effects, or even changes in solar radiation physics. However, no single explanation fully resolves the paradox. The faint young sun. Paradox remains a mystery, showing that our understanding of Earth's climate and early life conditions may still be incomplete. It forces us to reconsider how planets evolve and what makes life possible in extreme conditions. The dark matter paradox. The dark matter paradox arises from the fact that galaxies spin too fast for their visible mass, meaning there must be extra invisible matter holding them together. Based on Newtonian physics, galaxies should tear themselves apart because they don't have enough visible mass to generate the gravity required to keep them intact. But they don't, suggesting that some unseen mass, dark matter, is holding them together. Here's the paradox: dark matter has never been directly detected, yet it makes up 85% of the universe's mass, according to current models. If dark matter exists, why haven't we found the particles responsible for it? If dark matter doesn't exist, then Einstein's and Newton's theories of gravity might be incomplete, requiring new physics. Possible explanations include WIMPs, weakly interacting massive particles, a hypothetical form of dark matter, modified gravity, MOND, a radical idea suggesting that gravity itself behaves differently at cosmic scales. The paradox challenges fundamental physics. Either we haven't found most of the universe's mass, or our understanding of gravity itself is wrong. The solar supernova paradox. The solar supernova paradox asks, why hasn't our sun exploded like other stars? Most stars in the universe end their lives in violent supernova explosions, but our sun is expected to die in a much quieter way, shedding its outer layers gently and forming a white dwarf. But why? The paradox comes from the fact that the sun is relatively massive, yet it won't go supernova. Some smaller stars do explode, while some larger stars don't. The line between which stars explode and which don't is not fully understood. The reason lies in stellar mass thresholds. A star needs at least 8 times the sun's mass to explode as a supernova. However, recent studies suggest that binary star interactions, stellar composition, and rotation rates may also play a role. The paradox forces us to rethink stellar evolution. How do we know which stars will explode and which won't? And are we missing factors that determine a star's fate? The paradox of the absent-minded driver. The absent-minded driver paradox is a problem in decision theory that shows how rationality can fail when thinking ahead too much. A driver is approaching a fork in the road. Left leads home. Right leads to a detour, but another fork ahead gives one more chance to go home. If they miss both opportunities, they end up far from home. The paradox. If the driver always plans ahead rationally, they may decide, I'll take the second chance instead of the first. But when they reach the second fork, they think the same way and skip it too. In the end, they never go home, even though they had two chances. The lesson: overthinking and delaying decisions can lead to worse outcomes. This paradox appears in procrastination, delaying tasks thinking there's always time until it's too late. Investments, waiting for a better deal and missing opportunities altogether. AI and game theory. AI systems sometimes make suboptimal choices by assuming they can always correct later. It teaches that sometimes the best choice is to act early instead of waiting for a future opportunity that may never come. The Neutrino Paradox. The Neutrino Paradox comes from the strange behaviour of neutrinos, subatomic particles that barely interact with matter. Neutrinos pass through Earth almost undisturbed, with billions going through your body every second. Have mass, proven by experiments, but shouldn't according to the standard model of physics. Can change types, flavours, as they travel, something no other known particle does. The paradox is, if neutrinos have mass, does that mean our most fundamental theories of physics are incomplete? The standard model predicted neutrinos should be massless, but they aren't. The fact that they switch identities, neutrino oscillation, suggests unknown physics at play. Some experiments suggest weird anomalies, like sterile neutrinos, which might mean we haven't discovered all fundamental particles yet. The paradox challenges one of the most successful models in physics. Either the standard model is incomplete, or there are unknown forces or particles influencing neutrinos. Neutrinos may hold the key to solving deep mysteries about the universe, including why matter exists instead of antimatter. The paradox forces us to ask, is there a deeper layer of reality we haven't uncovered yet?